Hello, everyone. This is Mohammed Fakhouri, and today I would like to present you my master thesis project that has been won the CLGE Young Contest for 2022. My project titled Occlusion Screening using 3D city models as a reference database for mobile AR application. And I study Master of Photogrammetry and Geoinformatics at University of Applied Sciences in Stuttgart, Germany. So just to start with, what is actually augmented reality? So in augmented reality, we mean when we are overlaying a digital content over the environment, as you can see it in the image on the right, how the spaceship is just digitally superimposed on the image of the Louvre Museum. And when we have an interaction between the real object and the digital object, this is what we called mixed reality. So in the diagram below, you can see when we are starting in the far left, where we have only the real environment, everything that we can see with our own eyes. And on the far right, we have the virtual reality, where the scenario is designed and displayed by computers. And when we are speaking about mixed reality and augmented reality, we are somehow in the area between. So what is actually occlusion? So with occlusion, we are meaning like we are hiding some part of the digital object in order to preserve the line of sight. As you can see it in the image where we have no occlusion at all, in the image on the left, we can see that the cat is actually floating. But when we are cutting some part of this image, you can see like this, the cat is actually between the two sofa. And research shows it's highly effective 3DQ and a very good depth indicator. So for this research, we were using Microsoft HoloLens 2.0, which is a self-contained see-through mixed reality glasses, which has a 4 visible camera. This is used for tracking, including also an IMU, which include accelerometer, gyroscope, and magnetometer. And also we have in the middle a time-of-flight camera, which is basically used for 3D sensing. It's worth mentioning also that this glasses doesn't have a GNS or GPS. So basically, you're not able to identify where we are in the real world coordinate, which is an extra challenge for this project. So in order to have an occlusion, we need to understand what is the real environment is it. So we need to know what are the different objects that we have in the environment and where exactly they are. And as I said, like the time-of-flight camera will be useful in measuring the environment, but it's limited to only 5 meters and it might face some issues, especially when we are speaking about outdoor environments. So you can see in this example for indoor environment, we were able to map actually the indoor environment using the limited range up to 5 meters. But when we are speaking about outdoor, this is at an extra challenge. So in this project, we were aiming to create an immersive and representative augmented reality experience by hiding the digital content behind the real object. The main idea was to develop a public participation platform for urban planning projects, and this research was part of the ICT Mobility for ICT project. So to have a summary of what we are doing here, we were aiming to anchor the digital content to the real world and using the in-device scanning capability for dynamic object occlusion, and also enrich the scanned and reconstructed spatial map with the 3D building model to improve the outdoor occlusion effect. So our study area, it's in Leonhard Filter here in Stuttgart, and where we have a high urban density and lack of outdoor green meeting point. So here comes the need to introduce a new neighborhood center design in this area by featuring a less traffic environment. So different softwares and hardware were used in this study, starting with the main core, which is a Unity game engine, which was to create the whole scenario, and Visual Studio, which was used to compile actually the final result. A mixed reality toolkit which is the main SDK for the development with HoloLens, alongside with other softwares that was used and tested also during this research. So different data for this research we had, starting with the building model, which the actual representation of the buildings in the city. So we have a level of detail 1 building model, which means we have the footprint of the building and the height of the building, but we don't have any information about the roof. But since we have the model for the whole city, we need to filter first based on the area that we are interested in and convert all this building models from CLGML format to OBJ 3D mesh format. And definitely we need to take care of the issue of rotating around the x-axis, since different coordinate system is used in 3D computer graphic and in real life. And also we use the local coordinate system in this. So the main method where we are aiming to anchor the object or to place the object in their correct position, we were using a natural feature point detection using a simultaneous localization and mapping, which is shortly known as SLAM. So basically, we are detecting a feature point in the environment, and this feature point, the relation between it is known, and we can place the object based on this relationship with the feature point. So you can see it in the image on the right, like the different feature points, which is visualized in green. And we can place one anchor point and attach an object to it. So the anchor points was automatically distributed every 1.5 meters, roughly. And instead of anchoring each individual object, these points were actually used to anchor the whole scenario, and in order to use it in real time to optimize the whole scene. You can see here in this image, the building model, the LOD1 building model, and it's visualized in blue just for visualization. And this is basically this is used as a occlusion mask in this case. So basically you can see like we are aligning this model with the real life equivalent and use it as a mask. So any object behind it will not be rendered. In other words, it will be rendered with a 0 value, so it's not there and it will be hidden. And in this small video, you can see the developed applications and how we can enable and disable the augmentation of the content. You can see this is after the augmentation, and we will have less car in the environment. And yes, here you can see it also, where we have the car which is parked on the side of the road, and we are trying to introduce a car-free environment in this image. So as I said, the occlusion, we have two methods of dealing with the occlusion. The first one, which is based on the scanning, the data that we are scanning in real life. So you can see the image on the left where we have no occlusion. You can see actually the design is floating above the fountain. But when we are not rendering some part of this green design, you can see it's actually behind the fountain, which at the depth indicator. Same thing here happening with the building model, the one you previously saw. So you can see how it's aligning nicely with the real equivalent. And you can see the design without occlusion, it's floating actually over the building, which is not realistic. But when we have the occlusion enabled, you can see like some part of the design is not rendered, and which is very similar to how it's work in real life. Here you can see it, and you can compare with occlusion and without occlusion. And last but not least, in order to evaluate our proposed method, so we were aiming for two evaluation methods. The first one, which is based on performance. So you can see here we were aiming to achieve the highest frame rate possible with the HoloLens, and which is lead to less stress as it's expressed by lower blinking frequency. And you can see while we are loading a different triangles, different mesh segments, we still have the performance at around 60 frames per second on average. For that, we had a user study where we have some participants, to be precise, 14 participants. We started with a demo session and we give them the chance to try the final application and to try the occlusion shaders as well. And after that, we were asked about specific question. If they feel like this, if they are satisfied with this occlusion effect, and if they feel they have like a better depth perception, and also with the digital virtual content and the and it's mixed with the real environment, not as separated from the real environment, and you can see the positive feedback from all the users. So just to summarize, this study was mainly used to improve the occlusion shader by enriching the in-device spatial map with a 3D building model as occlusion is effect improved the user depth perceptions, and eventually this method can be transferred and applied in different studies area where we have a city model and building model. Thank you very much.